Very good evening to all the attendees who have joined us today in this special public lecture, which is being organized by the National Academy of Sciences, India, NASI, Delhi chapter, and the MHRD-Institution Innovation Council, Deen Dayal Upadhyaya College, University of Delhi, under the aegis of the DBT Star College program. Today we have with us Professor Carmen S. Menoni, who is the President, IEEE Photonics Society, and she'll be giving a talk on the lessons learned on optical coatings for gravitational wave interferometry. And as a customary, I'll introduce Professor Carmen. Professor Carmen is at university's distinguished professor in the Department of Electrical and Computer Engineering. And Professor Menoni's expertise is in optical and material science. Her research focuses on the development of novel interference coating architectures for power scaling of mid-infrared lasers. And this research is tailored to solve critical issues of laser materials interactions with light sources with unique pulse structures. Professor Menoni's research is also investigating and addressing key critical issues in the materials and coating structures that today limit the sensitivity gravitational wave interferometers. Professor Menoni is also involved using high brightness coherent beams of light of wavelengths between 10 to 50 nanometers for optics applications such as nanoscale imaging, ablation, and chemical imaging. She is a fellow of IEEE, Optical Society of America, American Physical Society, AAAS, and the SPI. She is the president of the IEEE Photonics Society. With these words, I request Professor Carmen to kindly share her screen and deliver her talk. Please go ahead, Carmen.
Well, I would like to thank Professor Saxena for this kind introduction and also for the opportunity to give this talk to this audience. I had never been in India, but I had students coming from India into my group, and I always enjoy these interactions because they were very well trained and always contributed a lot to advancing our knowledge in the research. So thank you. It's a pleasure to be here. It's a pleasure to be with all of you. So what I am going to present today is some research that is related to a materials study on amorphous oxides that are used for coatings for gravitational wave interferometers. So in 2016, a few years after the advanced LIGO detector was commissioned, there was the first observation of the gravitational waves that originated from the merger of two binary black holes, of two black holes. This was the beginning of the era of gravitational wave astrophysics. And in that now, we have another detector that provides astrophysical insights in a very different way. The most recent detection is actually a massive, the merger of two massive black holes, which seems to be the most distance that the LIGO-Virgo collaboration have detected. I have to mention that India is also part of this collaboration because there is a detector that is being built in India. So the gravitational wave detectors are interferometers, as I schematically show here. The arms of the interferometer are 4 kilometers long. And to give you an idea, when a gravitational wave perturbs space and time, the arms of the interferometers are displaced by amounts of the order of 10 to the minus 20 meters per square root hertz. This gives you an idea of the sensitivity that the instrument needs to have in order to detect gravitational waves. One of the major limitations in the sensitivity of these detectors is shown in here among all the different sources that produce noise, and is coating Brownian noise. In the test, at the end, in the interferometer, there are test masses that are coated with interference coatings that are a combination of titania, silica, and titania, doptantala, and silica. So there is noise in this interferometer, in these coatings, that is essentially that arises from internal friction that distorts the incoming laser wavefront. The interferometer operates at 1064 nanometer. And so it is this noise that actually adds to the signal, and at times it can actually overcome and shadow the gravitational wave signals. So I am part of the LIGO collaboration, and through this effort, we are looking at the materials properties that give rise to this internal friction, and we are looking at ways that we can overcome this internal friction. So what is the origin of internal friction? Well, the materials that we are working with are amorphous materials, and they are very complex. And the thermal noise is in these amorphous materials is associated with changes in the morphology or the bonding at the short and medium range order scales. These excitations are conceptualized as two level systems, as shown here in this plot, as shown here in this plot. So it is these transitions that contribute to elastic energy dissipation and then to Brownian noise. So how do we measure Brownian noise? Brownian noise or internal friction is measured with a technique that is called coating ring down measurements. So it's schematically shown here. The sample is placed in the center of this structure, and then is an electrical actuator essentially produces makes the sample oscillate, and so we see all of these oscillation modes, and then we look at the ring down signal from these oscillation modes. So this is the expression of the amplitude of the different modes of oscillation, and what we measure is the decay time that is related to the loss angle. The loss angle is the ratio of the imaginary to real parts of the Young modulus, and is a measure of the dissipated energy in the cavity. We do not do these measurements. We grow the materials on thin substrates that are 1 millimeter thick and 7.5 centimeters in diameter. And the measurements are carried out by Gabriele Vagente and collaborators at Caltech. But we do grow these materials. And these materials, as I mentioned, are amorphous, and they are typically grown by physical vapor deposition methods. In our case, we grow the materials by using ion beam sputtering. We have a system that is schematically shown here, which contains different targets, which can be biased simultaneously to, for example, make a mixture. What we do in order to adjust the cation ratio is the pulse that we apply to each of these targets is different. So this system offers very low deposition rates of, as I show here, of the order of 0.02 to 0.007 nanometers per second. And typically, we operate at a process pressure of 6 times 10 to the -4. So As I mentioned earlier, the coatings for advanced LIGO presently use a high index layer, which is a mixture of tantalum doped with titania and a low index layer of silicon dioxide. This is the low index material, this is the high index material. And in order to make a reflecting structure, we stack about 30 pairs or more of this sequence. Now, experiments have shown that it is the high index layer that has the highest mechanical loss at room temperature. So this is exactly the material that we have been studying with the goal to understand the origin of this internal friction and to develop new materials that will have lower internal friction. We have a goal to decrease mechanical loss by a factor of 2. We should have had already this material had it not been for COVID, for A+, which is the next generation of gravitational wave interferomet. So from now onwards, I am going to describe results that were obtained in my group and that focus on the study of tantalum pentoxide dope or mix with other oxides for, again, to study what are we want to know what are the changes in morphology, what are the changes in the optical properties, and ultimately how the mixing affects the mechanical loss of the coatings. So in this chart, what you see are results of X-ray diffraction that show the evolution of the morphology of the films with annealing. We studied 2 different cations concentration. One that is 0.27, which is very close to the value of the cation concentration of the best coatings that are used today, of the best tantalum titanium mixture used today, and another one that had a higher cation concentration of 0.53. So what these plots show is, again, the materials are amorphous as deposited, but when we anneal them, and the annealing process is critical to reduce mechanical loss, after about 700 C, we start to observe that the material crystallizes. When we analyze these peaks in the spectrum, we determine that these peaks correspond to a ternary alloy that has a monoclinic crystal structure. This alloy has not been seen before, and so this is the very first time that this transformation is identified, and you will see that it has importance in what I am going to show is the behavior of mechanical loss. Instead, if we looked at the other alloy with a higher cation concentration, we see that as we anneal, the very first observation of crystallization is at 500 degrees C, and this is this peak corresponds to titania crystallizing in the rutile phase. When we look at the material at the nanoscale, and we did that by using images from transmission electron microscopy, and these are shown here, we compare just plain tantalum pentoxide with the tantalum pentoxide mixed with titania with a cation ratio of 0.27%, and the alloy with a higher cation ratio. And what we see is that at 650 degrees C, which is just 50 degrees C below the temperature at which we show clear signs of crystallization, the material consists of grains or crystallites that are very small, they are nanometer size, mixed with some dark spots that you can see here better, and that are voids. So we conducted EELS spectroscopy on these samples, and what we found is that indeed the dark spaces are voids, but these voids actually contain argon. So this, again, is a very special morphology that is obtained right before the material crystallizes. So we conducted loss angle measurements on these materials with the technique that I showed you before. And what we learned is that in both cases, the two alloys reduce, this is shown here by the orange and green points. The two alloys reduce the mechanical loss of tantalum. This is the mechanical loss of, or the loss angle of tantalum as deposited film. But when we start increasing the temperature, we see that at about 500 degrees C, that is when we observe the crystallization of the higher content titanium sample, then the loss angle jumps significantly. And again, we typically see this increase when crystallization starts. But the lower value of mechanical loss, which is shown here, is obtained when in the sample that has a cation ratio of 0.27. And this at 600 degrees, again, is where we see this interesting morphology that contains nanocrystallites at voids. What it is interesting also is that at this annealing temperature, we also measure the lowest absorption loss in the coating, which is 4 parts per million. Just to give you an idea, these coatings that go into the mass of the interferometers have been optimized also with respect to absorption loss, because absorption loss also will cause noise in the interferometer. And the best results that have been obtained in terms of absorption loss at 1064 nanometers are 0.5 parts per million, which is an absolute, record low. So in the results that I just showed you, they were focused on adding titania to tantalum. So we ask ourselves, are there any other mixes that will give us also low mechanical loss? So we carried out a study in which we mixed tantalum pentoxide with other oxides, for example, niobium, hafnium, zinc oxide, alumina, and silicon dioxide, and others. And in all of these samples that we produce, we try to keep the cation ratio at about 20%. Of course, when we mix materials, then we are also modifying the optical properties. And what you see here is how the refractive index actually changes when we add different other oxides to tantalum. So for example, here when we add titanium, consistent with the law of mixtures, the refractive index at 1 micron increases. And when we add alumina, the refractive index decreases. And this again is another consideration in the design of the coatings, because we need a material that will have a large index contrast with silica to limit the number of layers that go into the coating structure. Because again, increasing the number of layers will increase the mechanical loss of the coating. So again, we conducted an extensive study of the evolution of the morphology of these compound mixtures as a function of temperature. And what you see here are the glancing instant X-ray diffraction spectra of all of these mixtures at the crystallization temperature. So if I take, for example, a hafnia tantala mixture, what we learned is that the addition of hafnia or the addition of zirconia to tantala, what it does is it increases the crystallization temperature of tantala. So the crystallization temperature of tantala is 650 degrees C. Notice that here we see it for the first time at 900 degrees C. There are some other alloys, like for example, scandia, in which we observed phase separation. And in this particular case, what the phase is identified as a tantalum suboxide. And so what this means is that there is competition between tantala and scandia that give rise to this formation of this suboxide. But what we showed is that, what we showed is that when we add zinc, we observe exactly the same behavior as with titania, in that we anneal the zinc and we identified a new phase, which is a zinc tantalum oxygen phase. One of the most recent works that one of the members of my group have done is actually predict these new phases that appear upon crystallization using density functional theory with data that is on the materials project. So this is work that is in progress, but we were very pleased because this is the very first time that the materials project has been used for amorphous materials. So what about the absorption loss on these mixtures? I tabulate here the absorption loss at 1064 nanometer, and these are on the annealed samples, annealed at a temperature that the sample is not crystallized, it's just below the crystallization temperature. The values of the absorption loss have been normalized to quarter wave thickness for comparison. This is undoped or just plain tantala. This is the absorption loss of tantala when it's mixed with titania. Again, this is our model material. And so adding titania also reduces the absorption loss. But when we add niobia, the absorption loss increases by about a factor of 2. Another, compound that is of interest is that of zinc, which I showed you that we form this ternary phase. And again, adding zinc is favorable to also reduce absorption loss. But the lowest absorption loss was obtained when we added alumina. So now what I am showing you here is how the loss angle varies with the different materials in the mix. And this is again at the temperatures that are the values are quoted at the temperature right below the crystallization temperature. And what these results show, again, that in most cases, the mechanical loss reduces when we mix tantala with other materials. However, with titania and with zinc, that these are the two materials in which we form these ternary alloys, we obtain the minimum value of the loss angle, which is consistent with what has been measured before, which is about 2.8 10 to the minus 4. So this has given us you know, some clues on how we have to search for new alloys. And this is the reason why this, you know, we started to use density functional theory with the data of the material project to try to identify new alloys. But so far we have titanium and zinc oxide as possible candidates. So this is the work that we have been doing in mixes. There is another alternative that is being explored within the LIGO collaboration, and actually this is this work on creating these nanolaminate structures is actually spearheaded by Innocenzo Pinto in Italy, and is and also there's work in Taiwan on this area that essentially has looked at the mechanical laws at cryogenic temperatures of nanolaminates. And nanolaminates are materials that are composed by nanometer thick layers of, for example, tantalum and titanium. So here we are depositing, for example, 6 nanometers thick tantalum and then 1.5 nanometers thick layer of silica or titanium. So we kept this thickness to control the cation concentration to about 20%, so that we would be able to compare the results of mechanical laws with the results of the mixtures. So we prepared two nanolaminates, one of tantalum and titanium and the other one of tantalum and silica. The thickness of these nanolaminates is typically selected to be quarter wave at 1064 nanometers. Again, we use the spattering method that I described at the beginning. And because we have these very low spattering rates, it is extremely, we can actually create very well-defined nanolaminates. So we looked at the evolution in the morphology of the nanolaminates with annealing, and we saw a very interesting behavior that is depicted here by the transmission electron micrograph images. So the top is the as deposited, there's a cross-section of the nanolaminate for the as deposited silica tantalum nanolaminate. And you can see how very well defined the layers in the nanolaminate are. When we anneal the sample to 650 degrees C, that we observe that the nanolaminate still is very well defined. These are similar results. In the bottom, I have similar results for tantalum doped with titanium. And this is the nanolaminate as deposited. And this is the nanolaminate annealed at 650 degrees C. And what you see here is that when we anneal the titanium tantalum nanolaminate, there is diffusion of the cations that actually blurs the interfaces. And now the nanolaminate is not well defined anymore. So in this particular case, there is mixing and homogenization. So we measured the mechanical loss of these samples. Actually, our colleague Gabriele Vagente measured these, obtained these results. And these results are plotted here. So we plot loss angle as a function of annealing temperature. The green dots are for the titanium tantalum nanolaminate. The blue dots are for the silica tantalum nanolaminate. So what you see here is that both nanolaminates have very similar values of the loss angle for the case of the as deposited sample. But when we start annealing, then we see that there is a sharper decrease in the mechanical loss in the titanium tantalum nanolaminate compared to the silica. And the silica, when we get to about 650 degrees C, the mechanical loss does not decrease any further. So again, what these results identified is that yes, the mechanical loss decreases with annealing, but the mechanisms that are coming into play and that are that are responsible for this reduction in mechanical loss may be very different. So we obtain the lowest mechanical loss or loss angle in the silica tantalum nanolaminate. So we compare using X-ray diffraction the two samples, and what you see here is the X-ray spectrum of the titania tantalum nanolaminate, that of the silica tantalum nanolaminate annealed at 800 degrees C. In both cases, we are at a temperature where we can observe crystallization, and the top spectrum is that of tantala annealed at 675 degrees C. So when we go to these high temperatures, we start seeing that the tantala starts to crystallize. However, what these analyses of this spectra show, we analyze the food width half maximum of this peak to actually determine the crystallized size. And what we see in the case of the silica tantalum nanolaminate is that the crystallized size in this case is of the order of the nanolaminate width, about 6 nanometers. Instead, in the titania tantalum nanolaminate, the peak is sharp because the nanocrystallite is much smaller, and this is possible because here we have mixing and of the two materials of the tantala and titania, and these, and as a result of this, we don't have a nanolaminate anymore. We have instead a mixture, as we had observed before. We carried out also X-ray photoelectron spectroscopy, and what this data showed us is that, again, in the titania tantalum nanolaminate at the surface, when we anneal, we can actually see signatures of titania, which again confirm that there is diffusion of titania into the tantala layer. So what these experiments and this study has showed us is that actually in the titania tantalum nanolaminate, it is this diffusion that is thermodynamically, that is allowed and that takes place to reduce the total energy of the system, that makes the material, transforms the material into a morphology that that has a lower mechanical loss. So this is what I wanted to present. So these studies have shown us that that essentially for reducing mechanical loss, we need to get an arrangement in which we form this mixture. And these results are confirmed both from our studies of mixtures and also from nanolaminates. Now, the ideal cation concentration for adding titania or zinc oxide, for example, is of the order of 20%, which is exactly what has been determined in titania doped tantala before. Now, the results on the nanolaminate, what they showed is that the nanolaminates do not give us a significantly different behavior than the mixtures in terms of mechanical loss, because we obtain the lowest mechanical loss when there is diffusion and mixture formation. But what we learned is that, again, not all nanolaminates are robust and stay intact to high temperature annealing. Rather, there are some in which, there is diffusion and mixture formation. So this is the end of my technical talk, but as Professor Saxena mentioned, I am serving as IEEE Photonics Society President, and I wanted to just give you a brief introduction and update to the society efforts. But before I do this, I want to thank both Lei Yang and Mariana Facio and my collaborators at Caltech, Gabriele Vagente, Elena Anajeva, and collaborators at Stanford, Ashot Markosian, Ricardo Basiri, and Martin Feyer. And this work is supported by the LIGO collaboration through the National Science Foundation. All right, so now let's begin into the IEEE Photonics Society and all of the programs that we have in within the society, which I really would like you to learn so that you can exploit within your chapter. So our society is a global network, is the home for a global network of scientists and engineers that are advancing lasers, optoelectronics, and photonics technology for the benefit of humanity. And as you are, you are part of this, you have formed chapters, and the chapters are the heart of the society. The chapters are the ones who bring participants that are established young professionals and students all together to further the goal of the professional society to advance knowledge in photonics for the benefit of society. So the chapters is also help us develop the volunteers. So this is why the role that you play is so important. We have over 150 chapters worldwide that promote the professional growth within the photonics community. And there are chapters carried out different activities that range from lectures and workshops like we are having right now to regional conferences and to also implement awards and scholarship for paper competitions. And this is very important. You should know this because the society can support you in all of these efforts. We are a society that cares deeply about globalization and about diversity and inclusion. And so we have volunteers that work very hard to diversify the participants within the society. And so you can see here examples of chapters in, for example, this chapter was formed in Kenya, and these are also chapters that were formed that are part of the society worldwide. We also have a program on women in photonics that encourages and supports the next generation of women in photonics. And again, we make big efforts in gender inclusion within the photonics community, and it's not, and in addition, to include our members in editorial boards, conference committees, and leadership positions. And we are also very passionate about young professionals because young professionals are the future. And so we have strong programs that allowed the students to transition after they graduate, when they transition into their career, to continue being engaged in the society. And so the starting point generally is when you are a student and when you are part of the chapter, but that is not the end. There is a lot of effort, and I am almost sure all of you that are established researchers and educators that are in the call have been through this path. So again, I show some of the activities that the Young Professional program offers. We have a meet-up program that stimulates the interaction of young professionals with established professionals and some signature events. And again, we also have a mentor match program that is very important and we are very proud of, and that we also implement with the students. We have resources to support the professional development of the members, like for example, webinars and also resources to write grants. And we also support the professional development of our members with publications and with conferences. And I list here all of the publications that the IEEE Photonics Society has at the moment. I was fortunate to be able to design IEEE Photonics Journal, that is the first online journal of the IEEE and became one of the first open access journals of IEEE. But we have a variety of journals that have offered topical diversity and at the same time allow you to publish in the most traditional way. So please consider publishing in the Photonics Society journals when your work. And I also would like to encourage you, just like Dr. Saxena reached to me and asked me whether I was interested in giving a talk, there is also a pool of distinguished lecturers who right now will be eager to give a talk in your seminar series. Normally we will all travel, but at these times we are just doing it from home. But please consider looking into this pool of exceptional researchers that have been identified as distinguished lecturers. And so we are, this is one of my last slides. We work hard to engage our members into becoming volunteers. And we do that worldwide. I mean, we have a network of volunteers that are heavily working in recruiting our members, young members, and established members into the society. So I see Dr. Saxena coming in, so I'm getting to the end of my talk. And this is my last slide, just to show that we also have some very extensive mentorship efforts. And in fact, in the last Photonics conference, I had a student from India Mira, whom I mentored through the conference, and so it was a great experience. So with that, I would like to close, and I would just like to mention that we need your help to grow. So please become engaged and join the efforts of the society in advancing professional development. And again, once more, I would like to thank you for this opportunity and for your attention.
Thank you. Thank you very much, Carmen. And before I ask Professor Katak to formally give closing remarks, I would like to take up a few questions. Shall I? Yeah, Carmen, can you hear me?
I can hear you, but I don't hear the question.
Okay, I'll take up the questions one by one. The first one is, can you elaborate more about the DFT calculations which are being performed?
Yes, I take, this, I don't know if you're, we use the materials project database and the DFT calculations within the materials projects database. We don't develop the model for the calculations. We just use what is on the materials database. And it's very interesting because this database has enormous information on all of the possible alloys that can be formed by mixing different materials. So I would like to encourage the person who asked this question to just visit the materials project database. All of this information, as I mentioned, is for crystalline materials, but it also applies to amorphous materials. So we don't invent anything. We just go to the materials database and we take that information and their tools to predict which are the phases that could crystallize whenever we mix two oxides.
Okay, I'll take up the next one. Why was the loss angle measured at different temperatures for different compounds?
The loss angle is measured at room temperature. The temperature that I showed is the temperature at which we anneal the samples. So the rule that we used is we knew where at what temperature each sample crystallizes. But when the sample starts to crystallize, the loss angle starts to go up. So we measure the loss angle in the sample, in the mixtures that were annealed 50 degrees C below the temperature at which we observe the onset of crystallization. And that onset of crystallization is different for different mixtures.
Okay, so the next one is, aluminum oxide is also showing promising results, but why only titanium oxide layer is used?
Oh, that's a very good question. Yes, correct. For aluminum oxide, adding aluminum oxide lowers the mechanical loss. And what we are interested in the problem of reducing loss angle or reducing mechanical loss in coatings for gravitational wave interferometers, there is another problem in which these two-level systems are also important to control, and that is on the insulating oxides in devices that are used to generate superconducting quantum bits. So in that particular case, maybe adding aluminum will work. But here is the main issue. When we add alumina has a lower index than tantala. So the mixture will have a lower refractive index at 1 micron than tantala. As a result of that, when you design the coating, you will need to add many more layers. And so adding many more layers has exactly the same effect increases mechanical loss. And so in reality, what we would like to have is a material that has a much higher index, and that's what titania gives us. Adding titania gives us this increase in the refractive index that also make us reduce the number of layers that we will use in the coating design. So we need to have a high index. We need to have an index, a refractive index of about 2 at 1 micron to make a good multilayer that will be comparable with the multilayers that are presently used.
Okay. Why the annealing breaks the titanium dioxide nanolaminate, but not the silicon dioxide?
Here is thermodynamics. It's because there is diffusion, and diffusion is the system that gets to a lowest. We lower the Gibbs free energy in the system when there is cation diffusion, and there is this ternary phase formation. So it's thermodynamically driven. This does not happen with silica. There is, it's essentially, this is exactly what we learned, and this is a very good question because it was a total new finding for us that again, reducing mechanical loss is not necessarily, associated with the structure of the material, but rather in the nanolaminate is a thermodynamically driven process.
Okay. How does one choose materials for fabricating reflectors? Is this process totally experimental, or do there exist any simulation technique to predict the optical properties of material?
We have tools to design coatings. We have programs that, you know, we essentially, and I also have a big program in developing interference coatings for petawatt type class lasers. And so there, the materials problems are very different. So we will choose different materials. For example, we normally make coatings with hafnium dioxide and silicon dioxide. But yes, we use programs. And again, the rule of thumb is you need to have high index contrast initially. So in all of our studies, what we first do is we do ellipsometry on the materials that we deposit, and then we grow. We use the ellipsometry to actually determine what is the value of the refractive index at the wavelength of interest. Typically, is the laser wavelength. For LIGO, is 1064. For some of the other work that we are doing is either 800 nanometers or 1053 nanometers. So, and then we choose the materials that will have the largest index contrast. And silica and alumina are typically the materials that are used as low index materials. And then tantala, titania, hafnia are the ones that are used as high index. And depending on the application, you will choose. I mean, in LIGO, we don't have issues of laser damage as we have with petawatt class lasers.
Okay, I'll take up the second last question now. How does the DFT work in order to give information on quantum modeling of molecules to determine these structures?
I don't know how to answer that question because I'm not a theorist, but it is it is a very established technique that essentially uses different potentials to calculate crystallographic arrangements. And okay. I would like to encourage the person who asked that question to go into the materials database.
Okay. There are two questions. I'll take up. I initially said it is the second last, but now I'll take the second last one. Is there any new development made with new technology, how the interference pattern modifies? And if we're trying to detect path of electron in double slit experiment in analogy with photons?
I don't think that this relates to, or yeah, I don't understand the question.
Okay, I'll pass it on to the next.
That it relates,
sure.
to the type of, either detecting gravitational waves or coatings. So.
Okay. So I'll take up the last one now. Tantalum dioxide forms cluster with zinc oxide and titanium dioxide. What spatial characteristics these oxides have which others don't? And what are the factors we are looking for?
Again, here is this mixing that occurs is thermodynamically driven, and annealing is provides the energy for these rearrangements to take place. What I did not mention at the beginning, I said, that the materials are amorphous, and indeed, from X-ray diffraction, from the X-ray diffraction point, they are amorphous. But when we deposit at very low temperature. So there is very little chemistry that can take place. So you can think that when we deposit these materials, we have tantala molecules, we may have tantala clusters, and the same titania and clusters and tantala, and very much like it happens in the nanolaminate, when we start to anneal with both zinc and when we add both zinc and titanium, these diffusion processes start to occur. And this, again, allow us to obtain a morphology that is unique and that is associated with the lowest mechanical laws. Now, I want to point out that there is modeling that is being carried out by collaborators at Stanford and University of Florida that are looking, the models are trying to predict what is the atomic rearrangement that actually give rise to the lowest mechanical laws. And they are doing this and also contrasting the results with silica, silicon dioxide and germanium dioxide, which are model ultra-stable classes. And so at the atomic scale, or at the short and medium range order, what these models predict is that there is a reorganization, that there is bond breaking and reorganization that occurs and that gives rise to organizations that reduce mechanical loss.
Okay, okay. So that's it from my side. I request Professor Ajoy Khatak, who's the chairman of the chapter, to kindly give some concluding remarks.
That was a very interesting talk, and one thing that Professor Menoni mentioned, and this is for the younger generation who are listening to this nice talk, is the fact that in India there is considerable activity associated with LIGO, and there's going to be a facility. Hopefully,
yes.
I'm able to see that in my lifetime, and therefore your talk becomes much more relevant. And we are so grateful to you for taking the time and speaking so early in the morning for all of us. The large number of questions that were asked and the comments that I see, people are very enthused. And that is our main purpose of the Academy, to enthuse the younger generation to take up science and take up basic science and physics and optics and other areas. So with that in mind, your talk is very relevant and very inspiring, and that you are doing with students from all parts of the country, including India. That was also very nice to see. So thank you very much. Have a great day ahead of you. Have a great year ahead of you. I hope we get through this COVID crisis. But this COVID crisis has brought in, I mean, Dr. Saxena has been working tirelessly to organize these webinars, and we have been able to hear outstanding lectures like that of yours. So one can never, one is always surprised to see the advantage that it has brought in. We can now attend SPIE conference and OSA conferences free of cost and listening to this thing, so they have all become online. So there are some advantages also that has come in with the COVID crisis, but we do hope it gets over very soon. Thank you very much.
Absolutely.
Again. And
it was a pleasure. I really I appreciate the opportunity, and I look forward to meeting you in person sometime. Whether
thank you. We'll do that.
Yeah,
we'll
absolutely.
Do that. And I hope you come and establish the LIGO facility in India, near Pune.
Oh yeah, oh yeah,
So Manoj, we should take that opportunity.
No, definitely, definitely.
At that time.
We would love to have you in India, in New Delhi next year, whenever things are more comfortable. That will be great. That will be great.
I'll be happy to visit. Thank you again for the invitation. It was a pleasure to meet you and to meet and to share our work and the Photonics Society efforts with all of you.